Ever wondered how a computer knows where to find the data it needs? The answer lies in a process called memory addressing. Picture it like a treasure map. Each piece of data is a treasure, and the memory address is the X that marks the spot. But instead of pirates and gold doubloons, we have CPUs and binary data. Memory addressing is the system that directs the computer to the exact location of data within its memory hierarchy. Think of the memory as a vast city, and the memory addresses as the specific street names and numbers. The computer uses these addresses to find and retrieve data efficiently. This process is crucial in computer architecture and plays a significant role in executing programs. Without it, the computer would be like a lost tourist, aimlessly wandering around, wasting precious time and energy. So how exactly does memory addressing work? Let's delve into the different types of memory addressing to understand better. First, we have direct addressing. In this mode, the operand's address is directly specified in the instruction. This is a straightforward way of accessing memory. To put it simply, when you use direct addressing, you're telling the computer exactly where to look for the data you need. It's like having a map with the exact location of a treasure marked. You don't need to solve any riddles or follow any complex paths, you just go straight to the spot. Now let's look at an assembly language example to illustrate its use. Consider this instruction, MOV AX. Here, we're moving the contents of memory location 1000 directly into the AX register. Just as simple as that. So what we've done is directly specify the address of the operand in the instruction. Simple, isn't it? But there's more. Let's move on to indirect addressing. Next up, we have indirect addressing. In this mode, the address of the operand is stored in a register or memory location. Now what does that mean? Simply put, rather than specifying the exact location of the data we want to access, we use a pointer stored in a register or memory location that tells us where to find our data. Let's consider an assembly language example. If we say MOV AX, it means move the contents of the memory location whose address is in BX to register AX. Here, BX is our pointer guiding us to the data we need. Why is this useful? Well, it provides flexibility. We can change BX to point to different locations, enabling us to manipulate different data without changing the instruction. That's indirect addressing for you, but wait, there's more. Now let's talk about base addressing and indexed addressing. Imagine you're at a party and you want to find a friend. Base addressing is like knowing that your friend is standing somewhere near the snack table. You go to the snack table, which is your base, and then you start looking around. In computer terms, the snack table is a base register, and looking around is adding a constant or displacement to that base register. So, for example, the assembly language instruction MOV AX is like saying, go to the snack table and then look 10 spaces to the right. Now, indexed addressing is a bit different. It's like knowing that your friend is the third person to the right of the snack table. The snack table is your index, and the number of people to the right is your displacement. So the instruction MOV AX is like saying, go to the snack table and then look 20 spaces to the left. The beauty of both base and indexed addressing is that they allow for dynamic memory addressing. You can find data at different locations depending on the values in the base or index registers and the added or subtracted displacement. Let's look at some examples. In base addressing, the instruction MOV AX moves the contents of the memory location, which is the sum of the value in the SI register and 10 into the AX register. In indexed addressing, MOV AX moves the contents of the memory location, which is the value in the DI register -20, into the AX register. These addressing modes are especially useful for handling arrays and tables in memory. Base addressing is often used when you have a starting point and want to go a certain distance from that point. Indexed addressing, on the other hand, is ideal when you have an index and want to find the data at that index. Base and indexed addressing are quite similar, aren't they? But each serves a unique purpose in memory addressing. Now that we've covered the basics, let's explore some more advanced memory addressing modes. Our first stop is the base register plus index addressing mode. In this mode, the effective address is formed by adding a constant, also known as displacement, to the sum of the contents of a base register and an index register. It's like having a two-in-one deal, a base register and an index register working together. An assembly language example would be MOV AX, which translates to moving the contents of the memory location at the address formed by adding BX, SI, and 10 to register AX. Next, we have the relative addressing mode. This mode is somewhat of a time traveler. The effective address here is formed by adding a constant to the address of the next instruction. It's like saying, jump to the instruction that's X steps away from this one. An assembly example of this would be JMP label, which means jump to the instruction labeled label. Last but certainly not least, we have the memory indirect with index and base register addressing mode. This mode is similar to the base register plus index addressing mode, but takes it a step further. Here, the effective address is formed by adding a constant to the sum of the contents of both a base register and an index register. It's like putting all the ingredients into a blender and getting a smoothie of addresses. An assembly language example of this mode would be MOV AX, which means move the contents of the memory location at the address formed by adding BX, SI, and 10 to register AX. These advanced addressing modes might seem complex, but they give programmers immense flexibility. By understanding and utilizing them, programmers can optimize code execution and make the most out of the computer's memory hierarchy. It's like having a toolbox full of unique tools, each with their special role in building efficient and effective programs. So don't shy away from these advanced modes. Embrace them, and you'll open up a world of possibilities in your programming journey. Last but not least, we have stack addressing. This type of memory addressing is a bit different from the ones we've discussed so far. In stack addressing, addresses are implicitly managed through stack operations. The stack, as you may know, is a special region of our computer's memory where data is stored and retrieved in a last-in first-out manner. So, what does that mean in practice? Well, let's consider an assembly language example. Picture the command push AX. This command pushes the contents of register AX onto the stack. When a push operation occurs, the data is stored at the location pointed to by the stack pointer, which is then automatically decremented. Conversely, a pop operation retrieves the last data pushed onto the stack, incrementing the stack pointer in the process. Stack addressing is a powerful tool that allows for efficient memory management. So we've covered a lot of ground today, haven't we? From the basics of memory addressing to its various types, we've delved into the nitty-gritty of this critical aspect of computer architecture. Let's do a quick recap. We kicked off with the definition of memory addressing, which is essentially the process of specifying the location of data in the computer's memory for reading or writing. We learned that it's a vital cog in the wheel of program execution. We then journeyed through the different types of memory addressing, starting with direct addressing, where the operand's address is directly specified in the instruction. We saw an example of this in assembly language, where we moved the contents of a specific memory location to a register. Next, we explored indirect addressing, where the address of the operand is stored in a register or memory location. This was followed by base and indexed addressing, which involved adding a constant to the contents of a base register, or an index register to form the effective address. We moved on to more advanced addressing modes, like base register plus index addressing, and memory indirect with index and base register addressing. These modes are a bit more complex, involving the addition of a constant to the sum of the contents of both a base register and an index register to form the effective address. Finally, we looked at stack addressing, where addresses are implicitly managed through stack operations like push and pop. Understanding these different addressing modes is crucial for efficient program execution. Depending on the instruction set architecture and the specific requirements of a program, we may choose one addressing mode over another. These modes provide flexibility in accessing data stored in registers or memory locations, and play a significant role in optimizing code execution. And with that, we've demystified the process of memory addressing. Remember, understanding these concepts is key to becoming a proficient programmer. Until next time, keep learning, keep exploring.